All right, let's kick things off with a statement that is, well, it's one of the weirdest, but also one of the most beautifully true ideas in all of math.
Yeah, you heard me right. Identical. And no, this isn't some kind of trick question or a riddle. It's a real, deep truth that actually opens up this whole amazing area of mathematics. It's all about figuring out what shape really means. So, how on earth is that possible?
Well, the answer is in this field called topology. The best way to think about it is it's the study of what stays the same about an object, even if you could stretch it, twist it, or totally deform it. In topology, we kind of just ignore things like distance and angles. We're looking for something deeper, the pure, unchangeable structure.
Okay, so to really get how this works, we've got to lay down the rules of the game first.
And here's the big idea, the main analogy you need to keep in your head. It's often called rubber sheet geometry. Just imagine that every single object, your mug, a donut, anything, isn't solid. Instead, it's made of this magical, infinitely stretchable rubber. That one idea, it's the key to everything.
So with this rubber object, you can do almost anything you want. You can stretch it, you can bend it, you can squish it down. But, and this is super important, there are a few forbidden moves. You absolutely cannot tear it. You can't poke a new hole in it, and you can't glue different parts of it together. Basically, its fundamental connectedness has to stay the same. Think about it. You can totally squish a rubber circle into a square, right? But you could never turn it into a figure eight without tearing and gluing. That's breaking the rule.
Now, this whole idea has a fancy mathematical name, of course. It's called a homeomorphism, and really that's just the formal way of proving two objects are topologically the same. It means there's a perfect one-to-one connection between them, there's no tearing involved, and, this is key, you can reverse the whole process perfectly. It's the absolute gold standard for saying two shapes are the same in topology.
Okay, so we've got the rules. How does this help us with our mug and our donut? Well, the very first clue is surprisingly simple. It really all comes down to counting the holes. To do that, we need to introduce a super important idea, a property of a shape that never changes. It's called its genus. And the intuitive way to think about genus is just the number of holes. That's pretty much it. The more formal definition is the number of cuts you can make along a closed loop without splitting the object in two. So for something like a sphere, the genus is 0, right? You can't cut it without splitting it. But for a donut, yeah, the genus is 1. That hole in the middle means you can make one full slice right through it and it's still one piece. It has one hole. Simple as that. And here it is, the big reveal. A coffee mug? It also has a genus of 1. Think about it. The main cut part is just like a dent in a ball. You can smooth it out. But the handle creates one single essential hole. That loop is its defining feature, topologically speaking. And this is not just some happy coincidence. There's an incredibly powerful rule in math called the classification theorem for surfaces. And what it says is, for these kinds of shapes, if they have the same genus, that's it. That's all you need. It proves they are topologically identical. They're in the same family. So that's the big idea, the conceptual proof. But topology is even cooler than that, because it also gives us a hard number, a numerical proof that just seals the deal completely. Okay, let's talk about something called the Euler characteristic. It's written with the Greek letter chi, and you can think of it like a unique fingerprint for a shape. The way you find it is you imagine the object is made of a mesh, right, with points or vertices, lines connecting them, edges, and the flat spots in between, faces. Then you just do some simple math. Take the number of vertices, subtract the number of edges, and add the number of faces.
And what's so amazing is that this number doesn't change. Look at this. A cube and a tetrahedron. They look totally different, right? But topologically, they're both just spheres. You could inflate one into the other. And check it out. When you run the numbers for either one, you get exactly 2. It doesn't matter how you draw the lines on the surface, the fingerprint, that number, stays the same because the underlying shape is the same.
And this is where it all connects in this really beautiful way. There's a master formula that directly links the number of holes, our genus, to this numerical fingerprint, the Euler characteristic. And the formula is simple. Chi equals 2 minus 2 times the genus.
So let's do it. Let's apply it to our problem. We already know that for both the coffee mug and the donut, the genus G is 1. So we just plug that into the formula. Chi equals 2 minus 2 times 1. And what do you get? You get 0 for both of them. Their numerical fingerprint is identical. This is it. This is the hard mathematical proof that they are, in fact, the same object.
Now, this might all seem like a really cool mathematical party trick, but these ideas, they have some seriously powerful uses in the real world today. There's this whole cutting-edge field called topological data analysis, or TDA for short, that uses these exact same principles. But instead of looking at coffee mugs, scientists use it to find the hidden shape in giant, messy, high-dimensional datasets. And because topology is so good at ignoring little unimportant details or noise and focusing only on the real underlying structure, it can find important patterns that other methods would completely miss.
And the impact is huge. We're talking about materials science, where it helps design brand new materials. In biology, it's used to understand the incredibly complex ways that DNA and proteins fold up. It's even used to analyze computer networks to find weak spots. In all these cases, it's about one thing: understanding the deep, hidden structure and connectivity.
So, what this all really means is that topology gives us a whole new way of looking at the world. It's like a new language for describing what really makes something, well, itself. It gets at the fundamental, stable structure of things, way beyond just their superficial appearance. It just goes to show you that sameness is a much deeper concept than we usually think. And it leaves you with this kind of amazing question, right? If something as everyday as a coffee mug is hiding its true mathematical identity, what other incredible hidden structures are all around us, just waiting for us to see them?